In our last video, we explored simple harmonic motion with the help of the ElectroPhy device. Today, we're diving into something just as fascinating: uniform circular motion. We will quantitatively measure centrifugal force under different conditions using our ElectroPhy modules. I have made this 3D acrylic model specifically for physics demonstrations. It features a geared motor, which is powered by this power supply. This is a fan. Let's attach it to the shaft of the motor. The fan is designed with holes at 5 cm and 10 cm distances from the center to mount the ElectroPhy device securely. Let's attach an ElectroPhy module to the fan using a 2 mm screw. Did you notice how the fan tilts downward due to the weight of the module? To balance it, we'll attach a second module to the opposite side. Now let's break down the physics behind our setup with the help of some animation. These are the three axes of the sensor, which move in sync with the rotation of the fan. The y-axis aligns with the radius, the x-axis is tangential, and the z-axis runs parallel to the axis of rotation. According to Newton's second law, force is the product of mass and acceleration. In circular motion, the centrifugal acceleration is given by A equals r omega square, where omega is the angular velocity. Therefore, centrifugal force, which acts outward, is directly proportional to the square of omega. The ElectroPhy will measure this acceleration along the y-axis, and by multiplying it by the mass of the module, 5.25 grams, we'll calculate the centrifugal force. But there's a key question: how do we measure the angular velocity? Our sensor's built-in gyroscope provides angular velocity readings along all three axes. However, the sensor's axes move with the fan. What we need are the global axes, which remain fixed in space. Luckily, the z-axis of the sensor and the global axis of rotation are aligned, allowing us to measure angular velocity accurately. This gives us both the centrifugal force along the y-axis and the angular velocity around the z-axis. Now our setup is ready. Let's move to the experiment. Now, let's turn on the ElectroPhy. I have sent the necessary commands to the ElectroPhy. Here we can see the real-time graph showing both the centrifugal force and the RPM. To remove the noise, we are applying FIR filter with cutoff frequency of 5 Hz. We'll control the fan's rotational speed by adjusting the motor's supply voltage. Now let's increase the voltage to raise the RPM to 75. Theoretically, centrifugal force at 70 RPM is around 28 millinewton. Now, the fan is rotating at 70 RPM and the centrifugal force measured by our ElectroPhy is approximately 29 millinewton. Now let's increase the angular speed to 140 RPM. As centrifugal force is directly proportional to the square of the angular velocity, doubling the RPM will increase the force to 4 times. And here we are. The RPM of the fan is at 140 and the force is indeed close to 4 times the 29, equal to 116 millinewton. This validates the relationship between centrifugal force and the square of the angular velocity using our ElectroPhy module. But what happens if the mass and angular velocity remain constant while the radius changes? To explore this, we've set up 2 ElectroPhy devices, one positioned at a 5 cm radius and the other at 10 cm. To make it easy to distinguish between the two, the device with the green LED will correspond to the green plot, while the device with the red LED will correspond to the red plot on our graph. Now let's power them up and measure the centrifugal force at 140 RPM. Theoretically, at 140 RPM, the force on the ElectroPhy at 10 cm should be 112 millinewtons, and for the one at 5 cm, it should be 56 millinewtons. Let's see what the actual measurements reveal. As the RPM reaches 140, we observe a force of 114 millinewtons for the device at 10 cm, and approximately 57 millinewtons for the one at 5 cm, exactly half of 114. This confirms that centrifugal force is directly proportional to the radius. You can see that one curve is moving faster than the other. This is a bug, and currently I'm debugging it. And there you have it. Our ElectroPhy modules have successfully demonstrated the principles of uniform circular motion. If you enjoyed the video, leave a comment below with your thoughts or ideas for future experiments using the ElectroPhy device and subscribe to my channel. See you in the next one.